have an unusual event where we are bringing two scholars to debate a topic of interest, both in philosophy and in the sciences. But before introducing our two participants today, I wanted to remind you of the events at the center in the coming days. On Friday, Arnon Levy, who is our senior visiting fellow, will be talking about explanation, and the title of his talk is An Understanding First View of Explanation. The talk will be in person at the Center for Philosophy of Science. And on Tuesday next week, yours truly, namely me, will be talking about Milgram's experiments on Tuesday at noon. You will hear why the obedience experiments developed by Milgram are in fact more informative than what some have said in recent years. We hope to see you at the center on Friday and Tuesday. Today, it's my great pleasure to introduce our two speakers, Nick Shea and John Krakauer. I'll start with Nick, who is professor of philosophy at the University of London. Many of you know Nick for his work in the philosophy of cognitive science. He has published extensively in many areas. I'll just mention his books. The first one was on Millikan a few years ago. And more recently, he has published a book which was very influential on representation, called Representation in Cognitive Science, published in 2018 with OUP. He has just finished a new book on concepts, and we were talking about it before the start of the meeting. The book should be out by late summer or fall at the latest. We are really looking forward to Nick's new book. John Krakauer is neuroscientist at Johns Hopkins University. He's a John C. Malone Professor of Neurology, Neuroscience, and Physical Medicine and Rehabilitation. He's Director of the Brain, Learning, Animation, and Movement, BLAM Laboratory, and has a few other titles. He has written extensively on motor learning, motor control, and related areas, both at the experimental but also at the theoretical level. One of the many amazing things about John is the fact that he's been willing to collaborate with us philosophers and to write with us. And indeed, he has a long history of engaging with different types of philosophers, from philosophers of language to philosophers of neuroscience. And it's always wonderful to have a neuroscientist or a scientist more broadly with such a great philosophical sensitivity. Thank you to both of you for joining us today for this debate about representations in neuroscience. The way the debate will be organized, that each speaker will have about 20 minutes, plus minus a few, and then there will be an exchange between Nick and John, Nick responding to John, John responding to Nick. And then we'll open the floor for question to the audience. If you have a question, please write your name, go down to the bottom of your screen, click on Q&A, write your name there, and I will promote you during the Q&A period to speaker so that you can ask your question directly to Nick and John. Nick, floor is yours. I will turn my camera off, but I will come back in about 20 minutes for the transition.
Great, thank you, Edouard. Thank you for putting this together and organizing it, and the Center for putting it on. And thanks to John for taking part. I just want to echo what Edouard said. So I very much enjoyed talking to John about representation, and he was kind enough to read and then review my book a few years ago, but that was a few years ago. So I'm very much looking forward to a new perspective and the way things have moved on since then. And echoing what Edouard said, it's an immense privilege as a philosopher who works in science or philosopher of science to talk to cutting edge scientists who are absolutely at the coalface, but having someone who's also so philosophically sophisticated is a real bonus. So I'm very much looking forward to today. And thank you to everyone else who's joining. I understand there's a whole room of people in Pittsburgh eating pizza, plus everyone else who's joined elsewhere. So I'm also looking forward to questions and comments there. So the central thing we're thinking about here is representation, which of course is this big fundamental explanatory tool in the mind sciences. And it was kind of a big important thing to cross to start explaining things in terms of representation. So representation has got to be something more than just a reflex or some circuit in the brain. It's a different explanatory level, a very special thing. And being able to use that thing in the sciences was ushered in, of course, in the cognitive revolution in the 1960s. And people then and still today are understandably skeptical that we should be able to find this very sophisticated thing in the messy wetware of the brain. So way back when, in a different life, I was a lawyer, a barrister, and I was training to be a barrister, following these other more senior barristers around. One day we were, as usual, in courtroom full of people, the very learned judge in his full bottom wig on the bench, and he invited the legal teams to go and see him in chambers. So we all took off our gowns and our wigs and trooped down endless little back alleys in the Victorian buildings and found ourselves in this kind of drafty office with piles of files and papers everywhere. And a harried looking, I was assuming a clerk sitting at a table with sifting all this paper, to which the person who was training me started chatting. And it gradually occurred to me that this other harried middle-aged lawyer, just like the ones I was following around, knew quite a lot about the case. And then it dawned on me that actually this was the judge. We weren't waiting to see the judge. They were discussing the case with the judge, but he was just a middle-aged, harried lawyer, just like the ones I was following around. Nothing special at all, except that when he walked through the oak panel doors, put on a full-bottom wig and a big red robe. And when he was dealing with the complexities of the law, he got to decide them rather than argue one side or the other. So when it comes to cognitive science, I think there is a species of representation which is also much less mysterious or much less profound than you might have been expecting. There's a kind of Wizard of Oz moment with that too. And I don't think it's the most sophisticated kind of representation. So I think in the human case, when we think about conscious representation, or if we think about beliefs and desires, there are lots of other things going on. But it is a kind of representation that's often appealed to explanatorily in the cognitive sciences. And is one of which I'm reasonably optimistic that we're beginning to give a philosophical account, both so that we can see why there are the kinds of things that are representations, features they have, what just ordinary naturalistic properties they have that make them representations, and how that supports much of the explanatory practice that you find in the cognitive sciences of appealing to representations to explain behavior, especially to explain successful behavior. So the characteristic explanatory grammar of explaining successful behavior by correctly representing features of the world and explaining failures of behavior by misrepresentation. So before I get into those philosophical theories, I just want to step back and think about the basic commitments, because this is going to be crucial when we think about whether this applies to neural representation at the neural level. And the basic commitment, which I think is going to be common ground to us in this debate and to most people in this thinking about this issue, is the one that was ushered in by the cognitive revolution. So suddenly in the mind sciences, we were allowed to explain behavior in terms of representations. And of course, there's a perfectly legitimate instrumentalist or a scripturalist way of doing that. There might be reasons why organisms or other systems behave as if they believe in desire. So Dennett has talked about that, for example, in philosophy. But there's also a more substantial sense, which I'm going to call a realist sense. And where there are real vehicles of representation, then you get a stronger explanatory framework. You get a deeper explanatory payoff. And what I mean by real vehicles of representation is that the things that bear content are physical particulars that play causal roles. They're caused by things in the world. They interact causally in internal processing, and they cause patterns of behavior. So they're, in that sense, they're like words on the page, or things going, pattern of light going down a fiber optic cable. They're physical particulars. They're interacting with other physical particulars in terms of their physical properties, but they're also bearable content. The standard assumption, and this would be familiar to almost everyone, I guess, was that even if we're thinking of representations as things with physical vehicles, it's very unlikely we'll be able to see them in the brain. There's no reason they would have to be scrutable in the brain. And there'll be lots of reasons for being skeptical that we would find them there. And then we'd have a picture where there were different levels of explanation. There was a neural level of explanation, and that would explain what's going on in the system that in some way or other realizes representations. But representations themselves wouldn't be scrutable in the neural goings on. There wouldn't be neural properties that would get into explaining patterns of things that happen with representations. And that's completely consistent with vehicle realism in the way that I was talking, because you'd still expect to find representations doing things that made sense in terms of their vehicle properties, like interfering with one another or explaining reaction times in terms of vehicle properties. It's just that it wasn't essential that those vehicle properties could be neural types of neural properties one way or the other. The commitment was just that they should be realized in the brain, or maybe brain body, or maybe brain body and world in some way or other. So it was kind of surprising that we started to find that there are neural vehicles. There are plausible cases where the bearers of representational content are scrutable in the brain, and we have an idea of what the things are that are interacting so as to cause the behavior that are carrying the representational content. So what kinds of things might they be, or do we find in these explanations? So on the left there, there's a neural network model that's explaining what this network's managing to do as a result of training in terms of activity across a layer of the network, clustering in different parts of the activation space, with the clusters going with contents. In neural networks, we can also, in philosophy, people have thought about the relevant bearers being polytopes in a high dimensional activation space. And on the right, there's a picture of neural data recorded in dorsomedial frontal cortex in monkeys performing a broadly decision task, looking at task relevant variables being carried by, and they claim represented by, dynamic trajectories in neural activation space. So something that has time as an additional component. So the bearer of content is something that exists over a temporal interval. So these are all different ways of going, and it needn't be that there's just one right answer. The realist commitment is that the thing that's carrying content has to be some real, non-semantically individual feature of what's going on. So the things that we say are interacting so as to cause behavior are things that describe the causal goings on in the system, in this case, the brain and how it interacts with the world, in a way that doesn't depend on thinking about the task that they're performing. And so that could be some, well, there are lots of candidates for features of distributed patterns of neural activation that could be like that. Most of the models that are doing this, most of the explanations that are doing this, look at neural firing rates as the basic bearer of content. So then we're looking at patterns of neural firing rates across some distributed layer of neurons. And that's resting on the assumption that when the firing rates across a layer of neurons are different, that makes a causal difference. That's to say, it will have been differently caused and it will have different downstream effects. But there are other things that could also be causally important in the brain, like fine-grained spike timing, and maybe some non-neural things. There could be computational role of the glia, or there might be things that are below the level of distributed patterns of activation, like computations going on in synapses. That's all consistent with realism, but almost all the work that is at the moment looking like it might vindicate some idea, some version of the neural representation hypothesis is looking at firing rates across assemblies of neurons. So I'm going to give an example of this to give you just a sense of how it works. But I've picked more or less at random from recent work that's coming out that's just methodologically interesting because it involves recording from a large array of neurons in humans. This is work looking at patients who are scheduled for neurosurgery for epilepsy and recording neural activity in different areas of the brain while they're performing a relatively simple reversal learning task that you see there on the right. So they've got to learn which button to press to get reward. And the reward schedule is there on the right of the screen. So you can see they've blocked out two of the pictures. But say when they see picture C, which is the car, they've got to learn that they've got to press the left button if they're going to get the reward. If they press the right button, they get it. And similarly, if they're looking at watermelons, they have to press the right button to get the reward. If they press the left again. And there are two contexts which aren't signaled to them. There's nothing on the screen to tell you which context you're in. But in the second context, all the rewards reverse. So potentially, as a subject in this experiment, once you've worked out what's going on, as soon as you press a button and don't get an expected reward, you can infer that you're actually in the other context and you have to reverse all your button presses, all your expectations about the. And what they were interested in was whether there is somewhere in the brain that's representing which context you're in that allows this inference so that when you switch context, the person knows what to do. So schematically, they're looking at it like this in the bottom left. Is there a way of looking at neural activity across a whole population of neurons, such that there's a dimension in that activity space that corresponds with which context you're in, so that in one context, you've got one set of ways of representing the relevant stimulus variables, like the button press and the stimulus and the contingencies. And then when you switch to the other context, that just allows you to immediately remap all the relevant parameters. And so they looked in activation in different areas of the brain, and specifically here in the hippocampus, to see how well they could train a classifier to decode context. And they found that it could indeed decode which context you're in. And then they separated between trials where the people performing the task succeeded in the reversal. That's to say, the first time after they pressed the wrong button, because the context had changed unbeknownst to them, did they on the very next trial infer, oh, well, I'm in the other context, and start getting it right again. Those are the inference present trials in the problem. And you can see in the inference present versus when people didn't make the inference on the first trial where they could, it's much easier for the classifier to decode from the population neural activity what the context is. And they also have another measure of the generalization form for this classifier, from which they infer that across this distributed pattern of activity in the hippocampus, there is a representation of which context the person is in, and that's the basis on which they're able to make the inference, so that when they learn they're in the different context, this pattern of activation represents them being in the other context, and that allows them to make the new appropriate mapping. So this fits with the kind of standard explanatory grammar of using correct representation to explain successful behavior. The representation here is figuring on as a causal intermediate on the route to getting the successful behavior. Something that's offstage and is offstage in most of the papers that discuss representation is there's got to be a lot of representations in the picture here for all of this to work. So the person somehow in their brain has to be representing not just which context they're in, but what the stimulus is, the button presses, so that's to say the potential actions, the stimulus response outcome contingencies, the outcomes, and so on. So the thing that we're focusing on here, which is the context, is just one representation amongst many, all of which are interacting computationally in order to produce the successful behavior. Another notable feature of this case is that the representations are just an intermediate between inputs and outputs. They're not decoupled from the world. And this, I think this will be a difference between John and I in the way that we're thinking about representation. So historically, especially when representation was very much contested, the best evidence for the existence of representation is in cases where representations seem to be playing a role that's decoupled from stimuli or decoupled from immediately reacting to the environment. And I think there are some of those cases where indeed explaining what's going on representationally gets an awful lot of explanatory power because there isn't an obvious kind of step-by-step input. This is going in the brain. This is the motor output. There's the movement. There isn't that kind of step-by-step story available. And that's not what's making a vehicle of content. So we've got all the explanatory question and the explanatory tools in place in a case like this one I've just shown you, where the representations are just acting as a non-decoupled kind of throughput on the way to explaining behavior. So I think, as against John, I'd argue that putting in a decoupling requirement, something to count as the representation, is taking something which is epistemically useful for identifying representations and elevating it to the level of a metaphysical. Okay, so that's to talk about the vehicles of content. Now I want to say a bit more about what's making them representations, and I'm not going to be able to do justice to this, but I'm just going to point at a bunch of ingredients that are shared between a kind of whole family of theories, of philosophical theories of representation, thinking about representation, including my own view. And these are broadly in the teleosemantic tradition, going back to Bruce Millikan and David Papineau, but adding in, certainly in my case, a stronger emphasis on how representations interact with each other and how they stand in exploitable relations to things in the world, which is a notion that I'm getting from Peter Godfrey Smith. So the kind of ingredients that go into a story about how what makes these internal vehicles representations is that they relate in some useful way to the world, like they correlate with properties in the world, or they correlate with things that are going in output, or maybe a bunch of them stand in a structural correspondence to things in the world. They interact in internal processing that's going to count as performing an algorithm, and that's all in the service of performing some task or function. And so I've given you a small sample of them. Many writers in philosophy are thinking like that. And there are also now writers in the cognitive sciences who are thinking about representation, and I think in a very similar way. And I think this family of theories, I mean, there's lots of debate about the details and how to exactly make them work. And I think this family of theories does make sense of the kind of representational explanation in the example. Mostly I've been thinking about relatively simple representations, but this does extend to representations that have got more complex structures. So where the internal states don't just correlate, but stand in some structural correspondence. And I think we found that in the case of representations in the hippocampus that are responsible for spatial navigation. And then the same neural structure, the same roughly the same kinds of neural structures can be used to stand for more abstract relations. So in the Whittington and colleagues paper, these were just arbitrary relations on a kind of notional two-dimensional grid between objects. And then a different kind of structure, one that's more familiar from language, like a language of thought type structures, we're beginning, cognitive neuroscience and cognitive computational neuroscience is beginning to find things in the brain that are scrutable, that are candidates for realizing those kinds of structures as well. So in the Franklin and Green paper, they're looking at a neural basis for serving the role of differentiating between agents and patients in understanding language or in thought. So differentiating between the thought dog bites man and the thought man bites dog. And then that preprint that I've put up there is a neural network model that gives a potential way of achieving that representationally in a kind of general purpose. And Edward kindly mentioned the book that I've just finished and should be coming out later this year. So this question of the different types of representation, the different levels of complexity and how they interact is something that I'm agonizing about there quite a bit. So that's in neuroscience. In artificial neural networks, we find the same kind of thing with the same kinds of explanations. So again, vehicles of content are some patterns in distributed patterns of activation. This is work now a couple of years ago in GPT-2, looking at the vehicles that might be responsible for storing information in a transformer model temporarily in order to answer a question. And they did a causal perturbation analysis to find where the information needed to solve to complete the sentence, the Space Needle is in downtown. They got a plausible indication of the information that we're talking about Seattle being present in one of these relatively early layers, and then being called upon by an attention head of a very late layer. More recent and quite impressive sounding result was a transformer model trained on just text input about moves that you would make in this board game, Fellow. So you're just telling it who's moved where. And they were able to decode the underlying board position and then rewrite that position. And then rewriting that position would get the model to make new predictions that were consistent of moves that were consistent with the new board position. Now, there's methodological questions about that, but that's an illustration of the kind of thing that's getting at representations as vehicles in these systems. And there's more recent work that's looking at linear decoding of these board positions. Although interestingly, in that work, it looks like, although in the early stage of the game, the board positions are being relied on to predict the moves, later on, they look like they're epiphenomenal with respect to the system being able to predict what moves. And there's a very good and interesting philosophical paper from Jacqueline Harding came out last year to try and spell out how it is that a philosophical theory of content could make sense of these kinds of things as representation. So finally, okay, I want to say two more things. So, but I'm conscious I'm already running out of time. So stepping back, there's another question we can ask, which is why are there representations? Why are there things that afford this kind of explanation? And that's a question I think has not been asked enough in philosophy. But I think there is a relatively straightforward answer, which is that computing over internal states that stand in exploitable relations to things in the environment is a way of producing outputs robustly. And first evolution by natural selection and then learning have targeted certain outputs. Firstly, survival and reproduction, but then more proximal things like getting food or getting back to a nest or a home or shelter. They've targeted the production of those things, and processing representations as a way of doing that. And I think because that's such a common feature of the natural world, this thing that I'm pointing to, which is a kind of characteristic pattern of relatively low level representational explanation, is something that works in very, very many natural settings. And finally, I wanted to end with a sense of there being a lot of interesting open questions about representation, right? I don't have any feeling like this is all sewn up and we know all the answers. And I just wanted to run quickly through a few. So there are questions about what should count as the relevant things to find in high dimensional activation space to be the vehicles of content, and whether sometimes there are reasons why you'd find that at the level of individual neurons. There's an important challenge once we're thinking about things like principal components in high level activation space about whether we're getting onto something that's genuinely causal, because there's very many different ways of dividing up patterns of activation. Are they all causal? And which ones, if not, and what are the principles? And Majrita Chiramuta has a paper in BJPS about this, and a really good book that's just about to come out that drills down into this question in a relatively skeptical vein, which I think is a really important challenge. Another open question for this whole framework is whether there's a additional level of explanation that's computational but not representational. For example, is there a neural circuit that's doing divisive normalization? And can we see that, and should we think about that in a way that is independent of whether it has any content or not? And then there's a couple of deeper critiques, which I take very seriously and I think will be productive. One is to say that, like lots of explanation in science, representational explanation is just a model, and there's lots of ways of having a relatively loose fit between model and target. So we shouldn't just be flat-footed realists. We should be open to there being all kinds of relations between our explanatory model that appeals to representation and the thing that it's purporting to explain. And finally, there's something which Edward is beginning to get involved in, which is thinking about whether there are other roles that representational talk or the concept of representation might be playing in science that don't turn on realism. Might it be doing other things? And those, he and Luis Favela had a nice set of results published last year in Frontiers, beginning to try and excavate how researchers think about the concept of representation. And I think that's an interesting first step towards understanding if there's a kind of larger variety of things going on here than just realism. So I better stop there, but try to offer you just a very quick sketch of a picture where we get some explanatory payoff for there being vehicles of representational content. There's a family of views that vindicate the idea of representations, and perhaps surprisingly, we're beginning to get some evidence that those things can be found in real neural structures, can be individuated neurally, hence there are neural representations. Thanks.
Thanks, Nick. John, I think the floor is yours now. But we can't see you. Your I think camera is off. But we can see your screen.
Can you see me now?
Yep, we do.
Okay. All right. Thank you, Nick. Thank you, Edward. Thank you, everybody. So I'm going to go as fast as I can. I might skip some slides just in the interest of time. I hope that's all right. So some preliminaries. Thinking happens. Thinking needs a particular kind of mental capacity that's called representation. These representations, as Nick said, have content. thinking is operation on these representations. The notions of grounding, embodiment, sensory motor culture, all attempts to get the semantics into these representations, into their computational syntax. But the point I want to make is the neural story will not mirror the mental story. In fact, I would say that the word representation should be banned from neural data. And I'll explain why I think that. So this is a slide I always borrow from Dan Dennett. I don't think he minds. I did it in front of him. And basically, this is two kinds of intelligence. There's the termite man that looks creepily like the Sagrada Familia on the left. And then you've got the real Sagrada Familia on the right by Gaudí. None of the termites that made that Sagrada Familia had it in their heads for it to look like that. It just turned out like that. Whereas Gaudí was very particular about the way that he wanted the Sagrada Familia to look. He had a notion in his mind of what it had to look like. Okay, so in other words, stark intelligence on the left without representations, intelligence on the right with very obvious representations in the head. Now, I want to just give credit to Bill Ramsey. You know, he and I are actually writing something on this topic, and this was a very influential book for me because he basically essentially considered representational behavior. When do you actually need to have a representation? And basically the idea is it's a representation when it functions as one. And he makes the point, which was very prescient, that actually the word representation is all over the place in precisely those behaviors where you don't need to invoke it at all, right? And he's very clear on this, and I can't recommend enough reading this book, which is still, in my view, essentially correct, that representation in neuroscience is all over the place and basically deflates the idea, which is mainly behavioral. He came up with the job description problem, and then he gave these, these examples of where one shouldn't use representation. Neurocorrelates are no more representational than a B cell releasing antibodies represents the infection. Weight patterns are predispositions to act, like a vase has the disposition of fragility, and so will easily break. It is not representing fragility. And then I put in, the motor cortex does not represent movement. Nothing in there is moving. Okay. So let's get to, let me see if I can just go into the right mode here. Okay. So here's the Sagrada Familia. What on earth is going on in the head of an architect or an artist to do this, right? This is what we really want to know. So let's get to representation as thought about by the philosophers. So Brentano thought of intentionality as primarily the capacity of the mind to be directed at things in the environment. And he thought of intentional in existence, the capacity of states of mind to be about things that are not present or not existing as one of the characteristic features of creatures that represent. This is Orlandi, 2020, in a very good article he wrote on representation. Now, Nick likes to say, oh, well, don't worry about offline representation, imagining things that don't exist, imagining things that yet haven't been built. That's just some, version of what's happening when the stimulus is present and the output is present. Well, I mean, that kind of deflationary argument is basically taking away the incredible power of real representation, which is responsible for all the things around you, including the Sagrada Familia. And so the offline capacity to represent things that don't even exist yet is precisely what we need to explain, not things coupled to sensory motor output. Mark Twain, apprenticed as a teenager to a Mississippi River pilot, later reported his mentors saying, you can only learn the shape of the river, and you learn it with such absolute certainty that you can always steer by the shape that's in your head and never mind the one that's before your eyes. Again, the point being the uncoupling. And keep the notion of shape in your head, pardon the pun, because I'll be talking about shape a little later. So here's a way that you do representation, all of you. Will this couch fit in your living room? Okay, so I'm assuming most of you are either at work or if you are in your living rooms, but you get the point. You can walk by the showroom, you can look in the window of the showroom, see that couch and go, love it. Shame it won't fit in my living room. You're basically able to conjure up in some way, let's not argue about format, your living room, and then do some kind of mixture of heuristic, mental rotation, measurement and determine that that couch is not going to fit in your living room. In fact, looking at it, I don't think it would fit in most people's living rooms. So just to talk about how dramatic this can be, let's go to some classic neuropsychology. So for those of you who may not know, there's this incredible condition of neglect, usually due to right parietal hemispheric lesions, where you basically start to neglect both peripersonal space and your own body. You basically don't register it and you don't act into it, okay? And this is an absolutely amazing experiment done way back now, I think in the 70s by Biziak and Luzzati, where they basically had people not just neglect, again, in front of the stimulus, like Nick is talking about, but just had them imagining themselves facing the Duomo in the piazza in Milan, and just simply then either draw it or mark out what they saw in their heads. In other words, simply say what's on the right of the Duomo, this shop, this cafe, and simply just tell us what the content of their imagined view would be if they were facing the Duomo. Okay? Now, what's remarkable is that they were able to talk about those things in their mind's eye that were on the right side of the Duomo, and they simply didn't even mention or see the ones on the left. They were neglecting. Okay? And then, ingeniously, what they did is that they said, okay, now we're going to turn you around, and we want you to imagine what things are from the other side. And lo and behold, they completely forgot the ones they'd remembered in the previous orientation and itemized all the others. Okay? Now, there couldn't be a more stark spatial representational piece of behavior, and that representation, wherever it is, got chopped in half in their own head. So basically, you had representational neglect. So here is a very stark example of the ability to get a representation in your head completely uncoupled and get it half right. Okay, so this is like a knife chopping in half the representation wherever it is. This is what we want to understand. Okay, and this is what we're struggling with, right? This is representational behavior where there's no other way to explain this behavior without invoking a representational capacity. So let's talk about shapes and planning, and this is some of the work that we've done. So in other words, this is an idea that, you know, this woman is thinking of the number 8, she conjures it up in her head, and then she draws the 8. Okay, this is also a little bit uncoupled, right? You think of the shape first, and then you motorically generate it. Okay, and now the point I'm going to make going forward is that you can completely uncouple these abilities, the execution ability from the ability to conjure up the shape in the first place. So this is a study that we did 8 years ago now. This is Aaron Wong. When he was a postdoc, he's now a professor in Philly and at Jefferson. And basically, it's a very simple experiment, right? You get shown 2 little gates, 2 little objects like that. And basically what you need to do is to get from one to the other without hitting the sides. Okay, like that. And then you can do a very simple experiment. As you can see, it's a curvy trajectory. The shape of the trajectory you need to make to get from the green to the blue without hitting the sides has a particular shape. Or you can give the people the answer. You just give them the gray line. So in other words, you give them the answer in front of them. They don't have to conjure it up, and then they can go. Now, critically, in both cases, at the time they go, everything vanishes from the screen. They no longer have a stimulus present, right? So whatever shape they conjure up, they're now going to have to generate it from in their head. They're not going to be able to look at any landmarks. And what's interesting, and you can see these trajectories, and they don't look any different whether you get the answer or whether you have to conjure up the shape yourself, right? Very beautiful sort of figure, if you ask me. Anyway. Now, what's interesting is that there's a huge reaction time cost to having to represent the shape you're going to execute versus being given the answer. It's almost 100 millisecond cost to having to do the representational work. All right. And what's also interesting is that reaction time is entirely at the representational level of stress. It is not related to the complexity of the movement you actually have to make, which can be determined by the number of turns in the trajectory, inflection points, zero crossings, things like that. Okay, so a very nice demonstration that you need to plan. In order to plan, you have to represent a shape. That representation of a shape can be conjured up in the absence of any stimuli on the screen, and then you can execute it. But that extra work has a very long, actually in psychology, reaction time cost of almost 100 milliseconds. So going back to the Twain quote, you seem to be able to represent shape. And I would argue, actually, that the ability to represent shape is what leads to tool use and all the abilities that humans do far, far better even than our closest primate cousins. Just to show you that there's a modularity to this, this is a study that Aaron also did in patients with left hemispheric stroke. And again, it speaks to the uncoupling of execution from representation. You basically can see them being asked to make fast point-to-point movements on the top, and the patients are fine doing it, right? Their motor control is perfectly normal. And yet when they're asked to copy a shape, the ones with the frontal premotor region are completely out of whack. They simply cannot imitate the shape. Okay? So in other words, and again, when you imitate, you get the shape is made by another human being, there's a delay, and then you have to conjure up the shape. Okay, and you can control the memory because they can do, you can basically give them tasks with the same interval and they're fine, and you can also see that subjects without these lesions have no problem executing the task. All right, so humans are odd. They have this ability to do representational work, and then when they have lesions, in this case, they get apraxia, they lose the ability to conjure up shapes, or they get neglect, they lose half of representational space in their mind. And this is just to show you imaging results, but I won't go through that now. And interestingly, this is a study recently by Stan Dehane, who basically did this very interesting study of shape, geometric shape regularity to do odd one out spotting. And interestingly, the humans were always sensitive to canonical abstract shape. The baboons in this case didn't notice it at all. Okay, so here there's a divide between being able to do a task, and the task is greatly simplified for the humans because they are attentive to abstract platonic shapes that help them do the task, whereas baboons have no such abstraction. So just quickly in terms of models, I will go through this quite fast. One of the ideas, and I think this was quite prominent in Nick's book, is that talking about internal models and representations is going to help us get to the kind of representational behavior and its neural basis that I've just described in all the cases I gave you, the highly cognitive ones. Okay, so what is a model? Daniel Wolpert, a motor control person, is a little simulator, or as ChatGPT says, a simplified representation or abstraction of a complex system, concept, or process. This helps us understand, analyze, predict, or interact with the real world. Now, I agree with ChatGPT. I don't agree with Daniel Wolpert in so much that simulation, forward models, internal models have led us completely astray. And in fact, I go so far as to say they don't exist. Here's a book about using models to understand the world. This is very much the rage these days. Oh, do LLMs have world models? We all need world models. You hear it. Yeah, LeCun uses it all the time. It's become a drumbeat. And quite frankly, I feel like there's a real confusion as to what's going on when that word is used. Here are two books. There was the one by Bill Ramsey with the emphasis on thought. And then there's Nick's book, which I did greatly enjoy, by the way, although I disagree with it in many places, with emphasis on sensory motor. You can sort of tell from Nick's talk already that you kind of want to tell a sensory motor story with the great desire to then be able to extrapolate in some magical way just by adding the word complex to juxtastic states. So the internal model principle, it's a very powerful one. This is work by Adrian Hayth, he's a former postdoc of mine who's now a professor at Hopkins and is doing really interesting work on this. And I'm just going to tell you that basically the point being made by Adrian is that the internal model principle is actually wrong on its face, and has actually led to its invocation in even sensory motor behavior when it didn't need to. So sort of ironically, and as a kind of parallel to Bill Ramsey saying that representation is invoked when there's no need to invoke it in many behaviors, same thing can be said for internal models. They're invoked all the time when they need not be invoked at all. And the internal model principle is basically this idea that you have a goal, you have a controller, you have a plant, you have observations. And the idea is if you want to avoid error altogether and you don't have full observation of the plant, you have to have some model of the dynamics of the plant to enable you to combine observations and your internal model in order to reach zero error. Okay, that was where the idea came from, that you have some simulator of the plant which allows you to get to zero error when you don't have full observation. This is just said in words. And, it was very influential. In fact, full disclosure, this is a paper quite highly cited of ours with Professor Shadmir going back to 2008, where this notion of an internal model and to a forward model was brought into motor neuroscience. This is what Daniel was talking about with the little simulator. So again, you have a goal, you have a policy, you send a command to the body, you simultaneously send your command to a forward model, and that forward model can be trained to predict the sensory consequences of your motor command, and that forward model can do state estimation, and then most importantly, somehow this forward model can be inverted to give you the feedback control policy. And that kind of model has been studied a lot by me and others using rotations where you basically rotate the cursor on a screen. You basically miss the first time you go, you don't see your hand, and then through a decremental process of adaptation, you finally zero in on the target. And this is implicit. You can fit exponentials to it, state-space models. This is a ubiquitous behavior in neuroscience. It's called adaptation. And very interestingly, and I won't have time to go to this experiment, it seems to be driven by sensory prediction errors that are unconscious rather than conscious target errors. And this is an experiment that we did going back to 2006. All I want you to know is there's a very powerful implicit sensory prediction error sensitive process thought to be cerebellar dependent, forward model dependent. So this was, and we wrote this ourselves when we wrote these papers, here is the forward model behavior par excellence, right? And it came up to, and it led to this orthodox diagram of the kind that I've showed you before. You have a control policy, you have a plant, you model the plant, and somehow by learning the forward model, which is in sensory coordinates, you invert the forward model and you get the control policy. Okay, so you've got a model in your head. It's a model of the world. You can use that model of the world to develop policies. It's just a short skip, hop, and a jump from this to full-blown representations. You could see why Nick might think that here's the sensory motor building block for real representation of the cognitive kind. Well, unfortunately, it's not the case. Okay, now again, I won't go into detail, but there's a study that we did at Hopkins, but basically we did an experiment where we wanted to sort of compete with this forward model inversion of learning versus direct policy learning, where basically you just go directly from the target error, you have a sensitivity derivative, and you basically learn through direct policy learning. Again, I won't go into the details now, but if you don't do the right kind of experiment, you won't be able to disambiguate these two ways. Alkes Joseph did this beautiful experiment where he basically compared rotations to mirror inversions. He showed that direct policy learning and forward model learning cannot be disambiguated in the classic adaptation experiment, but in a mirror inversion, you can actually disambiguate them. And essentially what you can show is that if you had a forward model that you could invert in order to learn the policy in the setting of a mirror inversion, you should be absolutely fine. You shouldn't have a problem. You should be able to deal with the error induced by the mirror. Whereas if you have a direct policy learning, you don't know how to put a negative sign in front of the sensitivity derivative, and you'll make bigger and bigger mistakes over time. And that's exactly what happens. People show no signs of having a forward model. They look like they just are learning directly. Okay, so if models and internal models from the sensory motor world existed, you could still argue, and I would, that they're not necessarily the stepping stones to full-blown representation, but they're not even your friend because they don't even exist in the sensory motor world. What internal states are sufficient. So just to tell you what I mean by that, here's Serena Williams serving. When you get served a tennis ball, especially by Serena, you're not going to be able to see it when it's in flight. Okay, it's too fast. So basically, you have to have some internal state that tracks the ball indirectly. So here I'm just saying the internal state is the sand in the hourglass. And basically, when the sand in the hourglass fills up completely, hit the ball. This sand representing the position of the ball in space is not an internal model, any more than a central pattern generator moving your legs has an internal model of your leg in the spinal cord circuitry. Okay, and then there are lots of other data showing that the neural equivalent of Serena Williams serving and the sand in the hourglass, I won't go through these, but basically neural structures can do that without having to invoke full-blown predictive forward models. Okay, so here's just a summary by Adrian that forward models and internal states uncouple. They're not equivalent in neuroscience, and those experiments do fine with internal states. No need to invoke forward models, models of the world, things in your head in these experiments, sensory motor experiments that you manipulate in order to get the behavior done. So mental representations exist. I've shown you with those, I hope, there's no real way to explain the couch, the neglect, the shapes without invoking them, but they're inferred from behavior. They're an explanandum for neuroscience. They're not explainants. They can have different formats, words, maps, images, once they externalize. They have content. They serve as stand-ins for something, no question. They guide stimulus-free performance. They're used for explicit deliberative thought. What about neural representations? These are problematically invoked as an explainers in neuroscience, as we heard from Nick. But I would argue, and there was actually a paper by Coelho Molo that Nick also mentioned in Venezzani, that neural data should be thought of non-representationally. The formats are different. The neural mechanisms of mental representation will not be structurally or conceptually like the mental representations themselves. And these are other recent papers that are very good about this. The danger of not realizing this is most apparent in how hippocampal replay is interpreted. Derived neural trajectories drawn by the experimenter are interpreted as a thing the mouse itself is imagining or looking at. That is simply not the case. It is a step too far to imbue neural data with representational qualities that are then meant to explain the representational behavior. Neural data obviously correlate and are going to be mechanistically related to the representational behavior that I've been discussing, but it is entirely misleading to call the neural data themselves representational. And in fact, Lauren Frank and others have shown that those replay pathways are almost certainly not simulations. And David Foster, who was cited by Nick, David's a very good friend of mine. In fact, he's coming here to Lisbon very soon. And he has admitted that just because you can show through neural recording that there was latent learning of maze structure that you can decode from the mouse, in no way implies that the mouse is conjuring up those trajectories or the maze itself, taking a look at them like the patient did of the square in Milan, and makes a decision. And in fact, there's a fantastic computational neuroscientist here at the Champly-Mo called Dan McNamee showing that you don't have to invoke that at all. But it just shows the power of the notion of representation, that it invades the explainers as an explainers, when in fact, what we need to do is to admit that we don't know what the neural format is. Now, as to looking for the neural correlates of representational behavior, this is a paper that David Barak and I wrote, and there's no doubt that you might begin to get insights into the neural correlates and the neural mechanisms of representational behavior. But it is a step too far to imbue the neural data with some intuitive representational structure of its own that somehow isomorphically maps onto the representational behavior evoked by the human. It's exactly the wrong way to go, in my view. So conclusions, there are human behaviors, at the very least, that are only consistent with positing true mental representations. Many intelligent behaviors, including in humans, qua Ramsey, do not need representations to explain them. Internal models and simulations do not exist. So they are not the foot in the door or the bridge to explaining representational behavior. Neural representations are not representations at all. The neural explanations of mental representation will not use representational intuitions and concepts. It will be more like the Word document on your screen is just zeros and ones in your computer's hardware. And I'll stop there. Thanks very much.
Thanks, John. Nick, let's take maybe 5 minutes each to exchange about 5-6 minutes to exchange about your reaction to each other's talk, and then we'll open the floor for broader discussion.
I'll be as quick as I can because I want to leave plenty of time for Q&A. So although it looks like we're at loggerheads, I think actually this kind of interaction is extremely productive, and I'm very sympathetic to a lot of your challenges, John. So the idea that often representational sophistication has been posited, which isn't there, and that this is a substantial and empirically difficult question, and we shouldn't jump in with both feet. I think that's a really good place to push, and there's a lot of overclaiming, and so it's very good to have people that are forcing us to be honest. And especially on these neural data where we've got all these new techniques for recording and analyzing, I think you're right. There's a very big danger of just reading the task back into the patterns of neural activity in a way that doesn't make the representations that are then posited at all explanatory. They're just kind of reading back into the neural activities, the task relevant variables, and they're not moving beyond the purely ascriptionist or instrumentalist way of thinking about representation. So I take those kinds of skepticism very seriously, and I think it's really productive to have people pushing on that. But I think there are two questions, one about which we disagree and one which we actually don't disagree. So when at the beginning you're getting us to imagine the sofa and rotate it and see whether it fits in our living room, I agree that's a different kind of thing, probably. And it's not my aim to get this simple species of representation to account for that kind of thing at all. So if that's the home of something that you want to call representation, then I'm not talking about that thing. And there's a big substantial task to try and explain that kind of thing philosophically. So then we're just not disagreeing. But then we're disagreeing about the simpler thing, because the simpler thing you say, that's not representation at all. And I want to say, no, there's a distinctively representational type pattern of explanation that involves internal states that somehow stand in this special relation to the world, where we can have correctness and incorrectness explaining success and failure. So I think that is the substantial disagreement. And your main argument there is that these are cases where we don't need to appeal to representation. So you agree with Bill Ramsey that that should be a criterion on the existence of representation. And I'm disagreeing about that. So just, I mean, there are several arguments, just let me pick out two. One is that I think it's a mistake to think that some natural property only exists when we think it's explanatory. So general relativity is needed to explain various things that happen in the heavens. It's not needed to explain the way that cars drive around the streets and so on. That's not a reason for thinking that space-time is not curved on planet Earth, or that general relativity is inapplicable there. It's just explanatorily not useful there. And I think the same can be true of some very simple cases of representation. But I also think that you're wrong to think that it's not explanatorily needed. So take the kind of case I was pointing to with the reversal learning task that patients were doing. There's an explanandum there, which just explaining things neurally doesn't get you, which is successful behavior, which is getting the 25 cents versus the 0 cents. That's something to be explained beyond the neural goings on in the brain and the pressing of the buttons. And I think we saw that with your Williams case. So Serena Williams serving. So there's one thing, someone might posit too rich an internal model, and that critique's well taken, that sometimes rich internal models are posited where they are not explanatorily useful. But it's a different thing to say, and we don't need representation at all. And I think that's to inflate the notion of representation and then say, that's the thing we don't need. You said, oh no, we can explain what's going on with Serena Williams in terms of an internal hourglass that's tracking where the ball is so that she can act. And again, we're explaining success, her returning this incredibly fast serve. We can explain that by it running through sand in the way that, and actually, you said represents where the ball is. And I think that's not a mistake. And it's not just tempting to use the term there, that's a species of representational explanation. There's an internal state whose correlation the system is relying on subpersonally so as to be able to hit the ball back to achieve success. So I think I'm not making claims about the richer thing. I think you're thinking that a simpler thing needs to be rich in order to do its explanatory work. And I want to hold on to the idea that there's something characteristically representational about those kinds of explanations. And that's the thing which I'm optimistic of, A, finding in the brain, and B, philosophical theories so far giving us a pretty good account of.
Yeah.
Yeah, I mean, again, I'm not, I'm part of this representational group, right? With Francis Fallon and Thomas Ryan and Kevin Mitchell and others. And, one doesn't want to sort of be the representation police in terms of how the word is used. And at the point that, Bill was making and that I'm making is that if you want representation to be a really interesting explanandum, then it comes into its own when it comes to the kind of behaviors I started with. If you want to talk about a simple mechanism in the body, like kidneys detecting pH or livers detecting toxins, and you're going to say that they represent pH and things like that, and that an hourglass represents the position of the ball, fine. If you want to use representation for that qualitatively different mechanism that will in no way help us get to representation. And in your book, you make it sound as though we will get from what you mainly cover in your book to doxastic states. I mean, it's implicit. I mean, the book was called Cognitive Representation in Cognitive Science. It was not called Representation in Sensory Motor Science. So in other words, I'm not, telling you what you were trying to impute, but all I'm saying is there is this belief that somehow these lower level forms of representation are somehow just different, are just related to the more complex ones, by degree, not by kind, and that we're just going to be able to get from here to there. And what I'm saying is that one of the reasons people had that confidence is that they thought that they weren't just having sequence of cascading of states, some reverberative mechanism. You actually had a rich internal model that you could simulate the world on, offline, consider path A and path B. And what I'm saying is the data do not support that rich internal model, which I think is what most people hope is the stepping stone to representation of the rich kind. So we're just left with this simple version that you're willing to say is unrelated to the higher complex one. Okay, but my guess would be that most people didn't realize that much more constrained project is at the heart of what you were doing.
Nick, do you want to follow up or?
Well, I'm conscious of time, but so one thing is to think that this simple version will account for the higher level. I'm not claiming that. Then you say it's unrelated to, and I'm not claiming that either. I think we don't yet understand these more sophisticated kinds of representation well enough, either to claim that it's just the same thing again, or to claim that it's entirely unrelated and we're going to have to start again. So epistemically, my view is at the moment we're somewhere in the middle.
Fair enough, but there's something. All I would say is that sometimes what we do is, as you say, we imbue with a little bit of surplus complexity the simple stuff that goes beyond what the data actually show. Like, for example, in the David Foster experiments, where they literally say in the papers, the mouse imagined where it will go next. So basically, cognitive language in surplus invades the experiments, which the experiments themselves do not merit. But the reason they do it is because they do hope that this is the beginning of a story about cognition. So, you're a lot more careful, it may seem. But the literature is replete with this surplus, meaning being thrown on top of results that do not merit that meaning.
Shall we open the floor for discussion, Nick, or do you want? Okay, good. Thank you, guys. So let me remind you how we're going to be working for the Q&A. If you have a question, please go to the Q&A, write your name, and I will, one after the other, promote you to participants so that you can ask your question directly to Nick and John, so I don't have to mediate between the things. It takes a few seconds for me to do that. So Andy, you will be the first one. You should be accepting the invitation you receive. All right, very good. Floor is yours. But you must turn your mic on.
All right. Hi. Hey, John.
Hi, Andy.
Say, I'm really confused. I think there seems to be, and you were hinting at it just now, a lot of confusion about the word representation. And I am, completely confused. People are all upset. They're saying there's no representation in the motor cortex. I mean, clearly from a signal processing point of view, if you just look at the information we're able to intercept at the motor cortex, clearly it's very correlated to the movement. Okay, I can, right? So it's
correlated.
Definition represented. Okay. Now, whether that's the job of the motor cortex and it has any other meaning, that's a completely different story. So I'm really confused by the word, I guess. And I was hoping you could straighten us out on that.
Yeah, I mean, for representation to be, as Bill Ramsey at the beginning of his book says, a deep concept in cognition, and I tried at the beginning, that if you want to imagine your living room, if you want to conjure up the Duomo in Milan, these are amazing offline abilities that you can plan to go to college years before you go. These are very impressive cognitive behaviors. Neural correlates of behaviors that are tied to the moment or to the stimulus. You use the word correlation. Absolutely. Look, I'm a motor control guy. You know that very well. I'm just saying that you don't need, and Bill Ramsey goes into great detail in his book about this, you don't need to invoke the notion of representation any more than a light, as he says, in a car that's telling you that your gas tank is almost empty. There's nowhere in that circuitry that has a representation of the gas tank. It's just an intermediary relay from the level of the gasoline to the light. And in that situation, which I think is directly like the motor cortex situation, you simply don't need to invoke a rich notion like representation, which is a rich model which you can operate offline and do work on before you go off and do something, like looking at the New York subway map. So representation can be used in that cheap, simple way as a stand-in for correlation. Neuroscientists do it all the time. You just did it. Or representation should be brought back to what it originally was supposed to mean, which is a much richer concept of an offline object that you can operate on instead of the real world. Now, if representation has become so ubiquitous that that distinction can no longer be invoked for that word, we're just going to have to do maybe what Nick does, put sophisticated in front of it, or complex in front of it, or some other qualifier. But there is a difference between what motor cortex does and what your brain is doing when you're imagining the couch in your living room.
So I think what it comes down to is when you're saying that you're making some assumptions about what you see and then coming up with a concept that relates to so-called consciousness, right? And that's what the problem is there's always a problem with definition when you talk about things like consciousness. Like if I was to put my electrodes in the brain and try to find consciousness, that would be, I think, equivalent to what you're saying as a representation, right? And then the question is, how do we know it if we found it, right? And so, I think we need to be careful with the terminology. Maybe your idea or maybe Nick's idea of a mental representation versus more of a engineering-based signal processing representation would be a good way to delineate the two ideas. I just would find as an investigator that would be very useful and remove some of the confusion that I have all the time.
Can I
I
just
think
answer
there's just a basic terminological issue here, which is in neurophysiology, representation is just standardly used in this much thinner sense in the way that you're using it, Andy. You explicitly said we can decode the information irrespective of whether it's being used for a task. And that's people can use the term as they like, and that's a standard use in neurophysiology. But I think that introduces just a completely standard confusion, because in other areas you talk about that just as information, and then in other bits of cognitive science, when people are doing representational explanation, it's clear that they're wanting something that's more substantial than that. So I think there is just something that's just a straight terminological confusion there between a well-established use in neurophysiology that doesn't require any of this, that's really just information, and then a whole bunch of richer uses that then John and I and others are arguing.
If I may, since there's a lot of people who want to talk to you, if I may move to the next question. Ivan, floor is yours. Thanks, Andy, for joining us.
Oh, okay. Thank you. Can you hear me?
Yeah.
Thank you for the talk. So my first question is for Nick. So I was wondering, you referred to neural particulars as particulars which need to be individuated non-semantically, right? But then I wonder, then what makes them representations? So in your talk, you said that there are three properties, so that they correlate with the world, they interact in internal processes, and they are in the service of performing some task, right? So this is what is supposed to make them representations.
Well, not really. I mean, I'm just gesturing at some things that are in a family of units. So, I mean, about all of those things, you have to say a lot more, that's a lot more specific, and then there'll be differences in order to get close to representation. I'm just pointing to some kind of structural things that our whole family of views will rely on each of those things.
Yeah, so I'm just not convinced of in which sense we can interpret neural particulars representations in the semantically loaded sense that philosophers want to give to representation. Right? They refer to something in the word. I just can't understand. So if you can, say something more about it. And on the other hand, there are other semantic theories which are not the standard ones. So for example, I'm thinking that constraint semantics. I don't know if you heard about it. These are a less semantically loaded semantic theory, which might be more easily applied to something like neural particulars, and understand in which sense these particulars are semantic, or have semantic properties. I just can't grasp how neural particulars individuated non-semantically can have semantic properties in the philosophically loaded sense.
Yeah. Well, it's not very philosophically loaded. So it's not, you said, referring to things. They're not doing that role. Just think about, and you can think about the example I gave with keeping track of one context versus another, or just take John's Serena Williams hourglass. So that runs down in a way that tracks where the ball is, and so she connects with the ball and it goes back over the net. Sometimes that will track down too fast, and she connects with the ball and the ball goes into the net. So so all the ingredients are, there's this internal hourglass that is supposed to correlate with where the ball is. She's relying on it, her motor system's relying on it in a way that depends on it correlating with the ball, where the ball is. And it just has a correctness condition. That's not any kind of rich reference. There are some cases where the world is the way that she's relying on it to be, and other cases where the world's not in the way that she's relying on it to be. And that gives us an explanation of the difference between the cases of her getting it right and her getting it wrong.
All right. I think we should leave it at that so that we can move on. Anna, floor is yours. Thanks, Ivan, for joining us.
Yeah, hey, thanks. That was great. Again, I'm getting more and more confused about when I should use the word representation and when I shouldn't. And I love this discussion. So I would suggest that if you sort of take the perspective that we say that for certain behavior, we have to assume that some information is used. then we are not saying whether this information must be accessible explicitly or whether this information can be just implicitly accessible. And if I hear John Krakauer talking about rich and cheap stuff, then I have the impression that you might say that whenever we do something motoric, it is very often automatic. It's very often something what is not explicitly accessible, and therefore it's cheap, and therefore maybe it's not worth to be called real representation. It is just an implicitly way to use information to operate your body. And on the other hand, if you want to know whether the sofa is fitting into your flat, then you have to have something what you can turn on explicitly by purpose. So you're not just on the flow, but you have to turn on the information, all the information you need to get to an opinion whether it's fitting. And then it would mean that if you are able to offline access information, then you would be happy to call this. Describe the difference between cheap and rich. And maybe
I mean, first of all, I mean, I've written a lot about explicit versus implicit, and that is the divide that I'm talking about here. You know, in the David Foster experiments, when the mouse is released to get the cheese in the maze, it is intentional, it is conscious, it wants that cheese. Okay? It's just not using a picture in its head. It's simply,
but it's using information.
It's executing a policy, right? Just like when you're walking, you intend to walk to the door, but you're not representing left, right in your head when you do it. You implement a walking policy. Your intentionality is to get to the door. So there are behaviors where you do invoke left, right, or something like that. That's representational behavior. The mouse and you walking to the door are very conscious, you're very intentional, you have a goal, but you're just enacting a policy. Okay, so there, and all I'm saying is that the explicit, implicit, unconscious, conscious, they're very interesting distinctions. They intersect in interesting ways with this notion of representation. But I'm saying you can have conscious, goal-directed representational behavior, and you can have conscious, goal-directed, non-representational behavior.
Yeah, I totally agree with that. All I wanted to say is that there is a difference. Certain kind of information are accessible on purpose, and other kinds of information, we cannot sort of decide, I want this information right now. And this is not the same thing like saying a behavior is unconscious or implicit. So I'm trying to make a difference between the accessibility properties we could talk about.
I'm just saying that accessibility of a particular kind of information that is representational, like you can conjure up to some degree what your apartment looks like, what's on the walls of your apartment. That's one kind of information. And I'm saying that is a unique representational ability that we have, just like bats are the only mammals that can do powered flight. We can do representation of this kind. And actually, it's interesting that people don't quite know how bats ended up with powered flight. And they now represent 50% of all mammalian species because it was a huge advantage for them to inhabit almost every niche. Our version of powered flight is this rich representational ability to imagine where our sofa will be. And all I'm saying is that we don't know how that works, but appeals to sensory motor behaviors won't get us there.
All right, I think we should leave it here because we're already getting to the 120 mark. David Barak at the center, can you join us before Jerry and Louise join us? Can you go to the computer, turn the cam on, and talk? David? 1, 2, 3, 4. All right, while David is doing that, Jerry, do you want to ask your question?
Yes, thank you very much for the very well-defined separation of ideas of the notion of representation. And it would appear to me that I was very surprised by the keeping the concept of memory very much in the background. Now, one of my projects in terms of representation is how to decipher a particular problem. And the problem of concern is how do you create a mental structure of a chemical structure in your mind from experimental data. So it's a sequence of operations are necessary to do this. And all of these are done in a sequential order in order to come up with a chemical structure from the data, from the semiotic data, if you would, coming in from the outside. So I don't see that big a conflict between the two speakers in this context. Rather, I see the number and frequency of needs to solve the problem depend on how often you must access memory in order to accomplish the goals that you set out in the experiments that are decided. So it's a question of how many tasks are you challenging in the cognitive recognition state of things in order to achieve the objectives. And the more tasks you have to accomplish, the longer time it's going to take you to do so in terms of neuronal processing.
Oh, I mean, I'll just say one quick thing. You know, I just find it interesting that human examples keep getting used. An experimenter imagining a chemical compound. In other words, this is exactly my point, is that we have this ability to imagine what a compound will look like after an experiment. Now, we can have a conversation about what we think humans are doing. All I'm saying is that it's very telling that human examples keep getting given because we keep talking about our ability to fly. And that's what we need to talk about. And I'm not going to study a mouse walking to understand a bat flying. And all I'm saying is you're absolutely right about the components that will be needed in order to do what you just said. Imagine a compound in your head after an experiment. But that's the human ability that I'm talking about, right? But neuroscientists keep using the word representation for far lesser behavior that, as I've argued, doesn't require invoking that notion at all.
But that
if I may, Jerry, if I may, we have actually a lot of people on the queue. Sure. Do you want to add something, or should I move to the next question?
Let's move on.
Okay. Thanks, Jerry, for joining us. David, floor is yours.
Hi, great. Thank you. I thought this was a wonderful interaction and presentation. My question is mostly for John, but Nick, feel free to jump in as you think appropriate. So first, I just want to make sure, John, that your position hasn't unusually changed from when we last chatted. You seem to imply by one line on one of your slides that there are no neural representations. And that's, if I understand correctly, just for these simpler things. You do think that there are going to be neural representations for the more sophisticated representation-hungry processes.
I'm saying, no, just to be clear what I mean. I'm actually saying that when we say neural representations, we're talking about the neural data that will help us understand how we do representational behavior. I don't think we have to call them representational themselves, right? So that's what I'm saying. So in other words, you know, look, it's a real mystery, right? I have a pen. The cortical spinal tract is sending signals down to my pen, and out of my pen comes a drawing. So at the moment that it came out of the tip of my pen, what was it? Where was that house before it came out of the tip of my pen? Now, in the corticospinal tract, there's no house in my corticospinal tract, right? So where's the house? So what I'm saying is of course there is a way to look at the neural data to get some insights of how I make a house come out of the tip of my pen. But I don't think it's very useful to say that I need to find the neural representation of the house. What I need to do is to understand how non-representational neural data can conjure up, just like there's no words in my computer when I close it. When I open up my Word document on my computer and words appear, there are no words inside my computer, right? There's some correlate of the words, but I would be very strange to say that the words are represented in my computer. They're represented at the moment of interaction with me. So I'm saying neural data, as we wrote in our paper, is useful, but I don't think it's some kind of isomorphic analog of the thing that it's doing in the representational behavior.
Even in the case of these representation hungry processes, like imagining things that are not in the here and now.
I'm saying that the format of the representation in the brain is not going to be some geometric version of the thing that is generated. I'm just saying, so in other words, it's not you shouldn't call it a representation. You should call it the neural mechanism of representational behavior, is what I'm saying.
But it's not identical to the representation.
No.
Okay, so we do diverge dramatically. And I do think this is an update in your view.
I would just say it's like that. I would say a JPEG and a pic and a photograph are different formats. And I wouldn't say a JPEG in its compressed form of zeros and ones is a picture.
Okay. But they're right, so they're different formats, but they're still representations.
One is a representation. The other one is a compressed, non-representational thing that will lead to representational behavior.
Nick, do you
want to join in?
I mean, we can agree that if you're drawing a picture, it's not because if you're drawing a house, it's not because you have a little picture of a house inside that you're copying out. But to go from there to say there's no representations that will explain what you're calling representational behavior, I think is a stretch. It's just it's not a representation of the kind that you're outputting. The representation isn't just a copy of the output behavior.
So why use the word?
Take another case where, well, because you want to explain this kind of thing. Suppose the person's doing something simpler and they're remembering where to reach, and you find that on the horizontal dimension they reach to the right points. On the vertical dimension, they get it wrong by a factor of 1.5. And then you find that there's some analog magnitude signals in the brain, the ones that correspond to the horizontal dimension correlate with the world, and something's gone wrong so that the ones that usually correspond to the vertical dimension are magnified by 1.5. Then you've got a hybrid explanation as to what's going wrong with respect to what they're doing along the vertical dimension. And it partly appeals to this neural property, and it partly appeals to the way that this neural property normally stands in relation to task-relevant features. And so to say what's gone wrong, you have to say, I mean, the simplest way of explaining what's gone wrong is that they're misrepresenting with respect to the displacement in the horizontal, in the vertical.
I just think it's a different use. I mean, I just
find
that
it's not just that they're doing that somewhere or other in the brain and it's realized by the brain. We can point to the part of the brain that's going wrong. In fact, we could directly intervene, make them misrepresent, and predict where their finger would go as a result.
So can I just have one question for you both. Why is it that when we do work on motor cortex, and motor cortex is responsible for moving, we don't say that the motor cortex is moving? But somehow, when we have representational behavior, we say the brain is representing. So why don't we, to be consistent, say that the motor cortex is moving? You've
just made a slide. We have behavior. We have action.
Right,
we don't say the brain's acting. We say that there are representations in the brain. They stand in an explanatory relation to action. So this category of representational behavior, you're imputing the representations into the action in a way that's completely illegitimate.
I'm just saying that representation, I find it very interesting, and I might turn out to be wrong, that there's this unbelievable desire to transplant our notions of representation and behavior into the neural data. And I don't know why we do that. I'm just saying, why can't we just say that we need to find out what the neural mechanisms are that lead to representational behavior and leave it at that?
Because if we're explaining something that we think demands representations, like planning a trip to Champlemoux in May, that seems to me to require that there's some referent of that term of my representation, and it's going on in my brain. It's some part of my brain that carries those contents. That's why that's not the here and now. This is the sophisticated representation hungry kind of process that it seems like you want to grant as requiring representation. And I don't understand why, and this is a change from your previous views, you wouldn't be willing to grant that there is something in the brain that we can say that's the representation. It could be a different format and so on and so forth. But don't you want to say there is that representation as opposed to just representational language that we're using?
I think the answer is no. He doesn't want to say. See if I can put words in your mouth, John. Anyway, we're reaching the mark of the 1:30, where by tradition we stop. But before reaching, I want to give Louise an opportunity, because Louise has been wonderfully patient. So Louise, floor is yours to end up this Q&A.
Hi, great discussion. I have a question for John. In fact, are correlations between neural data or neural mechanisms and behavior always irrelevant for representation?
No, I mean,
okay.
I think that we will get insight. We've gotten a lot of information about representational behavior from neuropsychology, from lesions, like I told you, in the epileptic patients, in the neglect patients. And it would be very odd, and this is the point that David and I made, that neural data would not just be on a horizontal plane of evidence, be another source of information to think about representational behavior. It'd be, one should send out all your hounds. You should look at neural data, you should look at behavioral data, look at lesion data. They should all one day help us explain what is going on when we do those remarkable behaviors that I described. All I'm saying is that the word representation means something to me in the behavior. It seems to just be a stand-in for that's the area where the neurons are doing something that leads to representational behavior. I don't think it does that much more work than correlation, causation, mechanism. That's all I'm saying. But of course, the neural data is important. I mean, I'm a neuroscientist, and I have to believe that it's useful to look at neural data.
Thank you.
Nick, do you want to add something before we
that's
conclude?
good.
All right. Thank you. It's been a lot of interest. We are reaching nearly 100 people joining us to listen to the two of you. So thanks to the two of you for this lively discussion. I think we should probably think of doing a follow-up with a slightly different format where we can actually also delve a bit deeper into this discussion. Apologies to the many of you who wanted to ask a question and I was unable to bring you for the discussion. We only have a short period and we stop at 1:30 by tradition. Thanks, Nick, again. Thanks, John, again. I hope to see both of you in person sooner than later. John, I hope to see you in New Orleans in a few months.
Absolutely. And I just want to thank Nick for being such a great interlocutor. And also, I really do hope that after this debate, it doesn't stop you from sending me your new book.
Oh, no, sure. Thank you too. As I said,
it was really wonderful.
It was super productive. And it's great to be doing it.
All right, wonderful. See you all, and thank you for this lively discussion. Bye.
Bye.